partners, BioConnect. I'm happy to be here to have a quick little talk to you about our 3D perfusion artificial capillary bioreactors. As everyone says, we have a very short period of time, so it may be most valuable for you to know. On our website, on the product page, we have an AI bot that searches the web as we sleep and finds all the articles that reference our products. So these 477 references will represent not just our EV papers, but also for monoclonal antibody production, recombinant protein production, parasitology, antibiotic PKPD, secretome. We have many different kinds of applications for our 3D perfusion artificial capillary bioreactors. Now, historically, we've done cell culture through the ages, and the initial attempts at cell culture were performed by Harrison in 1906 on a plasma clot, which is a 3D cell culture support. Not much happened for 80 years. In the last 40 years, we've been culturing cells on non-porous 2D supports in the presence of FBS, fetal bovine serum, not a physiologic way of culturing cells. This is not how they grow in vivo. And all the methods to greater or lesser degrees will subject the cells to what we call the feast or famine cycle, non-physiologic, constantly changing, non-homeostatic cell culture environment. So hollow fiber bioreactors are fundamentally different. It's based on the principle that each one of these fibers is like a little filter, shaped like a drinking straw, 200 microns in diameter. Those of you with black hair will recognize 200 microns. Blonde hair is going to be smaller in diameter. 10 micron wall thickness, so media flows through the insides of the fiber. We culture the cells on the outside of the fiber, just like they grow in vivo. It's fundamentally different in three ways from any other way of culturing cells. Extremely high surface area volume ratio. We have 200 square centimeters per milliliter volume. So imagine a film that's 50 microns thick. That's the kind of surface area volume ratio we have. It's the only way to grow cells at in vivo-like cell densities, 1 to 2 times 78 cells per mil. And when we grow cells at these kinds of densities, we have found they can generate their own microenvironment, much more physiologic way of culturing cells. Secondly, cells are bound to a porous support, not a non-porous plastic dish. This means we never have to split the cells. Passage number is irrelevant. We've grown a glioma cell for 2 years of continuous culture, hybridomas for a year, and we'll talk about stem cells in a minute. We also control the molecular cutoff so that small things like glucose and lactate can freely cross the fiber. Larger things like antibodies, extracellular vesicles, etc. cannot. So secreted EVs are concentrated to a high degree in the area outside the fibers that we call the extracapillary space. We can also use FBS or human platelet lysate in the circulating media only. And the factors that support cell growth will cross the fibers, and the EVs, the larger proteins, cannot cross the fiber. Some people talk about a cytocentric bioreactor where we're looking at the requirements of the cells. Because we're not splitting the cells, we can talk about a histocentric bioreactor in which the cells can maintain 3D structures and can maintain their own specific microenvironment for extended periods of time. Okay, we're going to skip through a few things. If it's an incubator, gas temperature is controlled by the incubator. The advantages are we have a concentrated product, all these things we can talk about. MSCs are very unique in that they do not proliferate in a hollow fiber bioreactor system. This is how they behave in vivo. We have to remind ourselves the amount of trash we generate for 10 to the 9 cells. We can see the large number of cells in the hollow fiber bioreactor, 2 to 4 coordinating 10 stacks into our medium-sized cartridge. They form spheroids when they're grown on the cartridge. The advantages here, we'll just run through these real quick. But I want to show this is our experiment where we show media optimization over 110 days of continuous culture, trying many different conditions, which I don't have time to talk about, but after 108 days, we can put in some rooster media. I'm not here to promote rooster media, but it's interesting. After 108 days, we can have a perk up in the cells and glucose consumption and EV production. So we also find with a non-proliferative cell that we can use transient techniques to generate a stable transfectant. We have our collaborator, Laura Perrin, who's been told by the NIH that she will never produce enough EVs to treat a patient. In this poster last year, we demonstrated a dose a day. We can generate a dose a day, move into our larger cartridge, 10 doses a day, run 10 cartridges at once, 100 doses a day. Now we're talking about 3,000 doses a month. So we go from impossible to 3,000 doses a month. Maybe some of you have seen your EV pellet. Maybe some of you haven't. This is 1 week's harvest from Jeff Franklin at Vanderbilt University, showing the kind of productivity of EVs that we can get. Okay, in summary, we have 3 seconds, so there we go. Also, we're a supplier on the International Space Station, just for you to know. And we are the most evolved way of culturing cells. Thank you very much for your time.